In this video, we're going to be talking about how the focal length can change for a lens as the temperature changes. And so the simplest idea is to have a thin lens. And if you have a very thin lens that focuses light to a point, light coming from this direction, you'll have the focal length, f. Now that focal length will change with temperature. And there will be two contributions. So if we think of that focal length changing a particular amount called delta f, that change in focal length, delta f, is equal to delta times f times delta t. So delta is the coefficient of thermal defocus. F is your focal length, and delta T is your change in temperature. Now if we take a closer look at delta, delta is a combination of two, or actually three material properties. So delta is defined as the thermal expansion coefficient of the lens material minus dN dt, where n is your index of refraction, and that times 1 over n absolute, which is your index of refraction, minus 1. So your dN dt, your n, and your alpha are all material properties. So thermal expansion coefficient, dN dt is the change in index of refraction with temperature. And this is the refractive index. This term looks very, very similar to the change in length of a material due to thermal expansion. So looking at this very simple example, again, this is just for a thin lens, so it's a very, very simple example, but it can demonstrate how these material properties can influence the coefficient of thermal defocus, which then influences the change in focal length. So if you look at different lens materials, you can start to see kind of different classifications. And if you compare their thermal expansion coefficient, their change in index of refraction with temperature, you can start to understand how they will affect your delta. So for example, infrared optic materials like chalcogenide glasses, as well as germanium and silicon, the thermal expansion coefficient is positive and has a small magnitude. But the change in index of refraction with temperature is very large, and it is also positive. And if you look at, let's not leave out the index of refraction. Typically the index of refraction, well, it always will be positive, but it'll be fairly small in comparison. So this term will be quite small. It's a fraction, essentially. So if you have a small thermal expansion coefficient that's positive, minus a large change in index of refraction with temperature, that is positive. Delta tends to be negative. And because the dN dt is so big, it's so much bigger than this thermal expansion coefficient for infrared optic materials, this can be quite large. Now for chalcogenide glasses, for example, this will be smaller because the dN dt will be smaller, but for silicon and germanium, this is quite large. If you compare that to polymers, you'll have a very large and positive coefficient of thermal expansion, and then you'll have a fairly medium to large negative dN dt. So this will actually be positive, but small as well. You'll have a very large positive delta because a positive thermal expansion coefficient that's large minus a negative dN dt makes this term positive. So for polymers, this is going to be a very large number. And then for different glasses, actually using this term, you can take a look. This is for different materials. NBK7, for example, very, very common material. Its thermal expansion coefficient is small, positive and quite small, at 7.1 ppm per degree C. Its dN dt is very small, at and positive, at 1.1 ppm per degree C. And its index of refraction is positive, and it is 1.5168. So your delta is actually going to be, for NBK7, is going to be, I believe it's going to be positive, and it's going to be small. So that's one of the advantages of this material. And so other glasses, you can do the same type of just eyeballing. Will this material react at temperature drastically just based off of this very simple equation?